So, how do we do engineering truss problems? Well, I won't lie and say they're not tricky, but I'll blast through them. Hopefully having a recording will help you remember what goes where. I'd like to take this moment to apologize for my handwriting. They've given us a new stylus this year, and all my videos from this point forward will not be nearly as good. So, here's a truss. It's pinned over here. So, at the pin, it can take a horizontal force. I don't know why that keeps happening. And a vertical force. And I'm calling them FAX and FAY because we're going to call this point A, this point up here B, this point up here C, and this point in the middle D. That is a truss right here, and that is a truss right there. It looks like there's just one that goes all the way across the bottom, but no, we have to pin it in the middle, otherwise this won't work properly. So this is a roller, meaning that it can only take a Y value, and a lot of people get confused on that. This point over here, and actually I want to relabel these. I keep going back and forth. I've never made up my mind. Fx at A, Fy at A, Fy at C. So this one can't take a moment. It's just a simple support. Things sit on it and it'll slide if you try and twist it. Over here it's pinned, so it can take a moment. But the sum of the moments about the point A have to equal 0. So what does this lead us to? Well, we look at these forces. We have this 500 force here, and it's in the negative direction. I'm not going to get into that right now. And it's 1, 2, 3 over. Then we have this force Yx, and you can see it's in opposite direction. This one's causing a turning of that. This one's causing a turning of that. So we have Fy of C times the distance 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you don't know where I'm getting the numbers from, each box is 1, so that's 1, that's 1, that's 1. And I'm just reading them off. And that has to equal 0. So if you do the math, you find that Fy of C equals 150. I'm going to leave all my units off. This one we're going to call inches and pounds. Each unit is an inch, and all the forces are in pounds. So I'm just going to leave them off for now, and I'll put them in at the very end. So actually, we'll put it in now for this one, 150 pounds. But otherwise, I'll just leave them off. Now, hopefully that makes sense. If it doesn't, I'm not sure what else I can do. The sum of all the moments have to be 0, otherwise this thing would be moving. It's a truss that's just sitting there. It would actually turn and bend, which does happen if the forces get enough, but we're going to assume these forces aren't so big that they'll bend the metal, which is actually the next step of engineering. Okay, how much moment, how much force? Oh, that's too much. We have to account for that. So all the forces have to be equal. So all the y's have to add up. So the sum of the y's have to be 0. In this case, that means Fya minus 500 plus Fyc, which we know. So we'll call that 150. Has to equal 0. That's the balance of forces. Now, up is positive. Down is negative, so that's why this gets a negative, and these two get positives, because we've drawn them that way. Now, if we did the math and found out when we're done, oh, they were supposed to be negative, then we'd go up and change the arrow. But looks like we did it right, because Fya equals 350 pounds. Now, for this one, this is kind of pointless. All the x's have to equal 0. Well, there's no other force. So Fxa, which is positive, drawn to the right, equals 0, done. I mean, there's no other force there, so we don't worry about it. Now we look at the individual joints. We've done the whole situation, and now we look at point A. We always draw the forces away, and this is joint AB, I believe. This is beam AB. We know that it has a vertical force of 350 and a horizontal force of 0. And there's also going to be a force in AD. So this is A. Now, this is annoying to people. They're like, why did you draw the arrows like that? We always draw them away. This indicates that the beams are in tension. If we get a negative answer, then we say they're in compression. And what we're showing is the force at the pin. So the beam is actually in tension. You might look at the arrow and say, no, it's in compression. Well, there's equal and opposite forces. The pin feels a pulling, which means that the beam feels a pushing, and it's in tension. Or other way around, I think I got that. No, the beam feels a pulling and the joint feels a pulling, and they're equal and opposite. Anyway, so now we do the whole around Y. The forces around of Y around A have to equal 0. So we get 350 plus AB, and if you saw the angle up top, it's sine of 53.138. And that has to equal 0. So we do the math and we find out that AB equals negative 437.5 pounds. So I'm going to go up here. And we had originally drawn it like that, and originally drawn it like that, but now we found out it's the other way. It's negative. So we do this, and we say that this beam is 437.5. Sorry, I need to write more neatly. 437.5. And we say it's in compression since the forces were the other way. And this force is going to be into the joint too. We're not going to worry about that much. So while we're at it, let's add all the x's up. Sum of the f of x's around A have to equal 0. We have a 0 force, kind of boring, plus the AD, because that's drawn to the right, so it's positive, plus AB, which we know now is 437.5. No, I didn't redraw it, so it's a negative. Now it's going the other way. Minus 437.5 cosine of 53.138. And that has to equal 0. Blast that out, we find that AD equals 262.5 pounds. So again, we go back up. We say this one equals 262.5. Since the sign didn't change, it's still in tension. Now, I'm going to do point D right here on the fly. I'm also going to erase this to get it out of the way, and I'll bring it back later, hopefully. If it's 500 down, then it's 500 up. And that's in tension, because I didn't change the direction. And if it's 262.5 that way, then it has to be 262, right up here, 262.5 this way, and it's also got to be in tension. Because the x's and the y's have to all equal, so there's nothing going on there of any turning forces. It's all vertical forces and horizontal forces. And they all have to equal because there's no angles, so everything's exactly the same. So this one is being pulled over at 262.5. FYC we know, so we can go and figure out what the beam BC here is. And we draw arrows like this, arrows like that. I could go figure out point B, but that's kind of a hassle. I'm not in the mood. So we'll do that. So let's use point C because that's the only beam we need to know is BC. So we come back here and we look at point C, and we have a beam going away, and this coming up at 150, and this coming over at 262.25, 262.5. And this is point C, and then this would be BC. So some of the y's have to equal 0. So if you do this, you would get 150 plus BC, you got to use the angle up there, sine of 29.745 equals 0. BC equals negative 302.3. So now we know we have our arrow backwards, and we put it on the other way. Also have it backwards up here. So we go back and put it on the other way. And we know this is 302.3, and since the arrows are flipped, compression. We can also go back and switch this one. We know this is wrong. Now I'm not going to do it, but I recommend you do. Try the balance of the forces at B, and you should find that they are all going to add up just right. If you want to do the x, you could say, well, f of x, oh, I can't believe I wrote a there, about point C has to equal 0, and we would have gotten 262.5, and now we know it's a minus because the arrow is the wrong way, plus, something wrong. Did I fix the arrow wrong way? No, I fixed the arrow right way. Oh, I drove this arrow wrong. Let's just go away from the joint. Negative 262.5 plus 302.3 cosine of 29.745 should equal 0, and it does. If you blast that out in your calculator, you'll see it's very, very close. And that's it. That's how we find what we're doing. It's very challenging and takes some practice. So good luck and happy engineering.